Okay, so let's move on to our next lesson. We are looking at the projectiles, and then we are looking at from there look at the momentum, and look at some kinetics. Okay, of course we'll look at what we call the these three for now. All right. So let's look at what we call coefficient of restitution. Coefficient of restitution. So coefficient of restitution. Let's say this body is moving. Okay. And then there's another body coming. Okay. When they collide. Then there's collision here. They collide. You have, so this is the initial velocity u1. This is u2. When they collide, you are going to move with v1, v2. Okay. Now coefficient of restitution seeks to measure, let's say, the kinetic energy before, then kinetic energy after impact or collision. So that we are doing that to see whether the kinetic energy that was before the collision is the same as the kinetic energy after the collision. You see that kinetic energy is proportional to your velocity. So we can look at velocity. So what coefficient of restitution is will be defined as, so the change in the initial velocities over the change in final velocities. So in that case, initial velocities, we have what? u1 and u2, that's initial. Then, so the change is the final on top, final on top. Then we have our initial here. Initial velocity. So we actually know that when they are starting, usually the energy that you start is going to be reduced. So we want to see by what fraction it has been reduced. If there's no reduction, then that is a kind of a perfect elastic collision. So it will have to be a perfect elastic collision. But if the energy is reduced at the end of the velocity that they are moving with at the end of collision is less than what they started with, then there has been some loss of energy. Okay, so there has been some loss of kinetic energy, and of course that will mean that is not an elastic kind of a collision. Okay, so in that case, we can use the coefficient of restitution to measure some kind of give us an idea as to whether it is elastic, inelastic. A perfect inelastic will mean this is almost zero, and therefore the coefficient of restitution is zero. As the final velocity they are moving with is almost zero. That is a perfect inelastic. Okay, collision. We come to that, and then a perfect elastic collision is when they move with either the exchange velocities, or they move with the same velocities as they were coming with. Okay, and that would be a perfect elastic collision. Okay, so let's see by formula. This is just going to be the final. So the final, where are the finals? Just the difference. So it's a difference. Difference means you can subtract anyone from there. Difference in velocities over difference in, so This is the final difference in final velocity, difference in initial velocity, which is the same as saying initial velocity, final velocities we have what? V1 minus V2 without sign. Okay, we are looking at the just the magnitude without sign. Okay, over once you started with V1 here, this is also the U1 minus U2, and that is the coefficient of substitution, right? Okay. So it gives you an idea, elastic, inelastic. So how much energy is lost? It's a measure. Okay, it gives you a measure. Okay. Now let's move on to the projectiles. I will briefly go over a few points and then I'm sure from there we can get the concept. So let's assume this is a clip and this is below here. Now let's say this is a cannon. It's a bullet to be shot. Okay. Now this is shot into the air. It goes like that and falls to the ground. Okay. So this is the projectile. So it makes a parabola kind of path. Okay, it's projected, it's shot, and then goes up. Now we can see that there will be an angle here. There will be an angle here. Let's call that angle theta. So it's shot with a certain angle theta. Now from this point to this point will be a certain distance s. Okay, so and this is about projectile. So we can be asked to do some calculations with respect to this. Of course, this is the maximum point that it gets to. The maximum point that it gets to. Okay, so it is shot with an initial velocity u. Okay, initial velocity u. Of course, when it is coming or when it is before it gets here, there will be some kind of initial and then horizontal. Okay, and then just before it hits the ground, to have some components here too. Okay, to have some velocities here, final velocities here. Okay, so you can look at it in that sense. So what will happen is you can actually see that this half will be equal to this half. There's that I didn't draw it in proportion. Let me draw it below. You actually see that this half is equal to this half. So that the time taken to get to the top here will be the same time taken to reach here. That can give you an idea. Okay, and then this is the distance it's going. So here, how do we get the equations? We already have our equations for linear motion. What we do is we already have a is equal to a is equal to v minus u over t. We have s is equal to u plus v over 2 times t. We have s is equal to ut plus half at squared. We have v squared is equal to u squared plus 2as. So these are the equations. So we use them to analyze the projectile equation. Right, so what we do is, first of all, we can look at vertical motion. The vertical motion. And look at the parameters as against the horizontal motion. Horizontal motion. And look at that. And then briefly count it. So for the vertical motion, let's say we start from here. The cannon is shot. Pull. Now as it's moving, this is the initial velocity u, we are giving that, and then we are saying that it is shot at an angle theta. This is the angle given to us. Remember, velocity is a vector quantity. So because it's a vector quantity, it has direction. Okay. Now it is moving in between. This is a vertical and this is a horizontal. It is moving in between the vertical and then the horizontal. So what you do is, as it is going, it will be changing position in the vertical and it will be changing position in the horizontal. Okay, but we are interested in the vertical motion, so let's focus on the vertical motion. How do we get the velocity of this, the part of, so u is between, is a vector, is between v and u. So the part of u which is in the vertical, we must know. If we know the part of u which is going in the vertical, we can derive equations using this one for vertical. If you know the part of u which is in the horizontal, you can derive equations following the equations here for the horizontal component. Okay. Right, so let's deal with the vertical component. Alright, so we said the initial velocity, so we have something like that. And this is u, this is theta. How do you get it? It's the same thing that we talked about in mathematics. When you have a vector quantity, let me draw it well. When you have a vector quantity like this, if you want to find its strength in the vertical, if you want to find its strength in this, you can use the Socrates method. Okay. So all you do is you try to make a right angle triangle from them. This is a right angle triangle. So this is the angle. Okay. This is the same as this. So what's the relationship between theta and then the vertical? The vertical is this. Okay. So you have the angle. This side is facing its opposite. Opposite is the relationship. And then this one has been given to us, u. So we have been given theta, we want h, and then we have been given u. So between theta and h is opposite, and u is the hypotenuse. So opposite and hypotenuse, what do we use? Sine. So it means from there, it means so this will be, let's say this is u in the vertical, u in the vertical direction. So you see that in this, that, and that we have said is they are related by what? Opposite and then hypotenuse, so which is sine. So it means that from here, sine theta is equal to opposite. Opposite is this u vertical over hypotenuse, which is u. So that the u vertical is equal to this u multiply this. So that we have u standing alone. It's equal to u sine theta. So it means the velocity in the vertical direction is what? U sine theta. Okay? Now that is the initial velocity. Now when the ball keeps on going, by the time it gets here, it stops because it gets to the highest point. At that point, the velocity in the vertical is no more going up. It's no more what? Going up. So that velocity, so this is going to be the initial, this is the same as the initial vertical velocity. Then the final vertical velocity. By the time we get here, the final vertical velocity is going to be 0. Okay, it's going to be 0. Before it will start coming down again in the opposite direction. It will start coming down again. Alright, so from here, if we want to write, let's say, an equation, if you look at this, which equation we have been giving you, V has also been given to us. So you can derive equations for these for C. So that when you are working things, you can easily work things out. So in terms of acceleration, now acceleration, when you are moving, this is motion against gravity. So acceleration, what will be causing or what will be changing the acceleration will be gravity, the acceleration due to gravity. So if you are moving up, the earth is pulling you. So the earth is going against your motion upwards. So acceleration becomes negative g. Okay, v has been given to us, that's the final velocity is u. Okay, and the time t can be calculated. So t, we are going to look at it. V is equal to 0 and u initial. U is the initial velocity, which is going to be what? Equal to what? Sine u vertical is equal to u sine what? We're going to u sine theta. Okay, so from this up to this point, we can do some calculations here. We can see that from here, our negative g will be equal to 0 minus what? U sine theta over t. Okay, because we have done all the substitutions. So that's the first equation. If you want to go to the second equation, S, which is the same as displacement. Okay, so we are looking at displacement. S will be equal to what? U is the initial velocity. We know it is what u sine theta. What's the final velocity? Is 0. We are looking at just this half. Okay, and then our t, and then we have our times t here. So this is the expression for this. That is considering from here to here alone. You can do an expression for this one too. S is equal to what? U which is what? U is u sine theta times t plus what? Half a is given as negative g, so times what? Negative g and t squared. So that will be the third equation. The fourth equation, v squared, by the time we get here, is 0. It's equal to what? U squared. So u sine theta squared plus what? 2 times negative g and then distance, s, or displacement, in this case displacement. So that's what you do. So once you get all that, this will give you the time. So this is just considering up to this point, the time it takes to get to this point. Okay, so that is the time. Okay, that is what is going to give. Let's assume if we didn't have this coming down, and then we had this is how the equation will go. Okay, so all that we have done, we are assuming this is the horizontal. Okay, we'll come to it when it is on the cliff. Okay, let's say this is the horizontal, so this is the ground. Let's assume this is the ground. This is the equation for the ground. But let's assume if this is a cliff, initially we should have made that assumption. Sorry for not. So let's assume this is a cliff. Okay, in that case, this is no longer the horizontal. So these are the equation. This equation that we have derived is for something like that. Okay. So once you know the time, like we said, the time taken to get here is the time that same time that you get here, right? So that will be it. Now let's look at where it is on the curve. It is not the horizontal, it's rather here. Let's see. In that case, when we are starting, there's a distance here already. That distance. Let's say this distance is S2. Okay, a vertical distance like that. Okay. So that will change our equation a little. It will change our equation a little. So we should remember that velocity and then displacement are vector quantities. So when you are dealing with that, you know. So let's say if we want to know the vertical from here, we want to know the first equation. Maybe it is for this equation. Then negative g is equal to final velocity. It remains so is 0. Final velocity is 0 plus u, which is minus u. Minus u, which is what? U sine theta, all this over t. So that will be the first equation if we are looking up to this point. Now if you come to the second equation, S displacement, the S, that displacement, this displacement that we are talking about, which is the same height, it will be initial, so it is going to be S0 plus what we are going to get upwards. What we are going to get upwards, because this is already starting from here, there's already an initial displacement from the ground. So S0, then we're going to add what? The distance. The distance is this. You can add that distance to this one as the distance. So that your initial velocity, you know your initial velocity, you know your final velocity, and then you know your time. Or somebody wants to say, okay, let's look at it this way from here. You can use this equation to distance, another distance, to find distance. You know the initial velocity, and then you go. Somebody will say you can use this one too. So any of them can go. Let's assume we are doing it for this one. So in that case, it's going to be this initial distance, okay? Then we're going to have what? U, which is sine theta. This is 0 plus 0 over 2. Okay, all this times t. Remember here, the t that we'll be talking about will be the time it will take to get to this point. Okay, so all you need to know is to have the time conscious of what you are doing. So the time that we are talking about is the time taken from here to get here. Okay, So that's the time we're talking about. Okay, the time taking. Time taking. That is where this thing is. We are not looking at the time taken to get to this point. Right? So we are just looking at half of the equation and then see. So this is how it will go. And then you can do that to get all the other equations. But let's see something. If you want to get to the end of this point, then you have to modify the equations. You should know what you are dealing with. So all the four equations, you can try to get them for projectiles by looking at it initially from up to this point. Gives you an idea, and then you can look at it that way. So let's see up to the end of this one, the vertical. Okay. So in terms of vertical, we are going to have distance is equal to the S0 plus what the distance traveled upwards, or let's say vertical distance. So the vertical distance is from here to this point. Okay. So our initial, we can put which of the equations we want to put there. The distance is a constant. So we are adding this distance that we travel. It's going to be, we can use S is equal to U plus what? A over 2 times T. If you put that one there, you're going to have what? U sine theta. Because we have already said U is sine theta, initial velocity, final velocity, by the time you get to 0. So 0. Okay. Right. So that is 0. So plus 0 over 2, and you have T. So this will be the final distance or displacement. Okay. So we have initial coming in, then we have this one adding on. Okay. So if we, so there is a time. Okay, there is a time taken to get to that point. If you put this one there. Now, if we assume to put we look at so this will be the distance, vertical distance. Vertical distance. Okay. So this initial times what we'll get here. Of course, this T then will be the time taken for this one. Time taken to get to the up there. Now let's look at for the whole. So that's the vertical, the highest we can go. Okay, that's the vertical, the highest we can go. So is this one. As this, of course, this portion alone is going upwards. Okay. So in that case, because it's going upwards, you can look at it as your positive. Okay, as your positive distance. Okay, the displacement is positive. And then we have initial this plus the positive is T, so that. Now let's look at the horizontal distance. Horizontal. The horizontal distance, how are we going to get it? Okay. The horizontal distance should be the component of U in the horizontal. So component of U in the horizontal. Let's look at it. Here we are interested in this one. So this is U. We are interested in this one. So the relationship between this angle. So the relationship between this angle and this. So we are giving adjacent angle and hypotenuse. Adjacent hypotenuse. So that is cos. So it means cos theta is equal to adjacent, which is what? The initial U in the horizontal over hypotenuse, which is U. So that the initial U in the horizontal is equal to U cos theta. So that the velocity here is U cos theta. The velocity in the horizontal direction is U cos theta. So we have to put that one in place of this. So here the distance between you is S, and that is going to be less what straight away the distance is going to be. Distance is given. We can look at any of the formulas that have been given to us. So here, if we are putting this one there, it's going to be what? U cos theta. What's our final velocity? The final velocity, do we know the final velocity? We don't know the final velocity. So let's assume the final velocity is being in the horizontal direction. It will have a certain v. Okay, over 2 times our time. That will be the whole time taken. Okay, that will be the whole time taken. So this can be an expression. But remember, this time we are using it for the whole time. If we are using it for the whole time, then this distance at that point, this is how it's coming. From here to that point. Okay, and that's the distance. Now, if we want to find time, we can do it. We can do it. For instance, if we were looking at it from this direction, from the horizontal direction, we can find t from the horizontal component. You can see that from this equation, if we want to look at the whole movement downwards, okay, then this s1, if this t, we are looking at this t, the initial velocity, the final velocity we don't know, then okay, let's put it that if assume for the total from up to down, from up to down, you realize that by the time this goes up and comes down, what will be the distance? It is going to be this distance that we have covered plus s. So s will be equal to the distance up. This one is the distance up. Okay, let's say that is the t, but it's just going to be the t up. Okay, so let's say this whole thing, s0 plus us sine theta over 2t. Of course, this t can be t1 because it's not going to be our total time t. Okay, so this is giving us the vertical distance. So this one, and then what has gone on here. Okay, right, and that is what we had for this one. That is the initial one if we express it on this. Now let's look at it from this angle too. Alright, so let's assume, like we said, this is the equation. This is a general equation. Now let's assume that we are looking at the vertical component alone. The vertical component alone, let's say moving upwards, going up, so as it goes, and it comes down. So this distance traveled, okay, or displacement, this displacement. By the time it goes up and comes down, it's zero, because there will be no displacement. The time taken, it should have started with initial velocity u sine theta, that's the initial velocity. So that is what it's going with. But the acceleration is negative g, that's negative g which is stopping it. And then the time taken to get to this end here, which is the time for this movement, is the t that we have given. So this will be the equation. This will be the equation. This will be the equation if there were no height here. But if we have this height already in there, then it becomes this and that. Because we have added this height as well. So that will be this for the same time t. So this will be for just this kind of projectile, and then this will be for the kind of projectile we can have like that. Okay, so this is the vertical component. Okay, once you have this, you can make your deductions and then get them. So you can get your t from here, maybe by the quadratic equation. When you get your t, to get your horizontal distance will be equal to your velocity times your t. Okay, if you have two velocities, then it is the average velocity times t. So if you know our time, the horizontal velocity is this. Okay, now the horizontal velocity goes like that. It is not affected by any gravity. It's not going to be changed by any acceleration. So it is constant. So it's just going to be u cos theta times t. How do you get your t? You can get your t from the vertical equation. You can calculate your t. You know this, angle, you know this one, you know j, sorry. So you can use this one, you can use this equation, get your t, which is the total distance. When you get your t, you add it here, you put it here, and then it will give you the horizontal displacement or time, horizontal displacement or distance. Right. So in summary, let me just make it this way so that the understanding is made simple. We can have this projectile so that it is very simple for us to this end. Okay, this is the initial velocity u, the vertical. Then let's look at another one. This is another projectile. If it has been short like that, it goes just showing you how you can easily remember. Okay, this is the point. Right, so let's go with this one. So this will be the vertical distance, okay? This is horizontal. We have said that this angle, there's an angle between this and that. There's another angle here. So let's call this angle that it makes with the horizontal, theta. Now, if we are resolving, this is theta, this is u, this is theta. Okay? Because this is u, here must also be a velocity component. So that will be the velocity in the vertical. Okay? Okay. So we are saying that from the formula S is equal to ut plus half at squared. For this kind of projectile, this is a horizontal ground, then you have it going up, the ball going up. S, let's look at the vertical component again. S will be equal to u. Our u becomes what? The component here, this is theta and what? Theta and then vertical. So theta and opposite. So we are going to use sign. So it's going to be here is going to be sine theta is equal to this one, the vertical over hypotenuse, which is u. So vertical velocity will become u sine theta, then we multiply by t plus half acceleration due to gravity. Because this is going up, acceleration due to gravity is going to be negative g, and then we will have our t squared. So this is the equation for this one. Okay, so this is the equation for this one. Okay, so if you are just looking at if this is the initial velocity, if you are looking at the distance, if you are looking at, let's say, from here, that is the time taken for this one to get to this one. That's the time. Somebody can say, okay, I just want to look at half. If you want to look at half, then it's half of this distance. Half of s is equal to u sine theta times half of t, because that's the time, the first time that we were using was for the total to go up and come down. So half of t. What we are saying t is the time up to this point. Okay, half of t plus half times negative g. So that will be what half of t squared. Okay, something like that. Okay, so this is how, so it depends on where you are choosing your point up to the end. This is the equation. But remember, up to the end, from here up to here, by the time it goes up and comes down, the change in the vertical distance will be equal to 0. So S will become 0 and is equal to u sine theta t plus